Yeah, welcome to Office of Technology Transition Discovery National Lab Discovery Series. Today you're going to hear about Electro 3D and additive manufacturing process. So let's kick it on over to our intro slide here. So I'm Carl Walzak. I'm from Sandia National Labs. I've been a member of Sandia National Labs since 2017, working on a range of different projects from advanced and exploratory systems, looking at surety mechanisms, components, and materials, to understanding how to take technology from a very immature stage or research state to a more production type setting. So I've had a diverse set of experiences at Sandia. One of the projects that I work on here was awarded an R&D 100 award in 2023. That's called Electro 3D, and that's what the focus of the presentation is going to be on today. Prior to Sandia, I was at LBL, Lawrence Berkeley National Lab, at the Joint Center for Artificial Photosynthesis, JCAP. And then, yeah, prior to that, I was working on my PhD in finishing up in 2010 with Craig Friedrich. So the technology that we're focusing in on today is called Electro 3D. This technology was not developed in a closet. There's a bunch of different contributors to this technology at different phases of the development. And during the early stages, it was part of an LDRD program through Sandia National Labs. And the core members of that team were Brian Perdue, Adam Cook, John Haidt, Garrett Williams, Jesse Duran, Jacob Bates, and Jonathan Coleman. So they really helped with a range of different aspects of this technology, from project management to ideation to electrochemistry, just a lot of different aspects of it. And today, a lot of this work is being conducted by myself, Morgan Hamby, Hannah Powers, Debbie Hutchins, and Mikey Garrett. So again, a very diverse team that has helped bring this technology to where you'll see it in these slides today. So let's keep on rolling. So additive manufacturing is a technology that is transforming the world of manufacturing today, and it's going to continue to have a very impactful future. Everything from medical to automotive to aerospace to satellites, you name it, there's the potential to transform how manufacturing is conducted today versus how it could be conducted in the future. So again, Electro 3D, it's a electrochemical additive manufacturing process, and this differs from what's currently available or what's currently in the market. A lot of metal printing has been conducted with thermochemical processes, whether that be powders or wires, and they're either sintered with heat or lasers. And a lot of that, there's been a ton of great work, and there's different strengths to each of these processes. So I'm just going to show you a slightly different method for producing metals, and that's with electrochemistry. So to adopt additive manufacturing into your technology, you need to consider a lot of things, from qualification, from materials to parts to printers. All those aspects of making something likely need to be qualified, just depending on the level of technology that your component, your part, is being inserted into. So for satellites or high consequence environments, for example, there could be different requirements than something just that's going to be used in a toy or something else. So qualification is very dependent on the application and the parts that they're being used for. Additive manufacturing traditionally has had challenges creating fully dense parts, creating parts on a cost and speed and resolution that are suitable for the demands of whatever you might be producing, and then doing this all up at scale. So traditionally, or the thought is, additive manufacturing, it can be used for prototyping. Well, I would say now we're more transitioning towards production type thoughts and discussions, and We're going to talk a little bit more about electrochemical or 3D printing on these next couple slides, so we'll get more into this technology. So here's a video. Electro 3D, it's a electrochemical 3D printer. And how it works, we really leverage a lot of electrochemistry, electroplating materials and techniques that have been developed over the years, centuries. But what we have done to innovate is to put it into a 3D printing platform that allows for localized, selective deposition of the material of choice. So what we were really proving this out on was thermoelectric materials. However, we did demonstrate nickel, copper, gradients of nickel, copper, and there's a ton of other potential materials and combination of materials that we can make with this technology.
Harvesting waste heat is a critical issue for energy conservation and efficient energy use. So we're focused here on developing a novel process to make thermoelectric devices. And this is challenging because traditional methods to make thermoelectric devices are difficult to scale to the appropriate dimensions that we need to be efficient in this process. So we are taking advantage of our ability to electrodeposit these materials and our experience at Sandia with additive manufacturing, and combine those two things together in a new process that allows us to synthesize these materials ready to use in the form factor that makes them most implementable as devices.
The way our system is different, and what makes it really a game changer, is that our technology does not require the part that's being printed on to be submerged into a bath. So a lot of these electroplating baths are either really acidic or really alkaline, and that really limits what materials you can actually plate onto or grow structures onto. So with our technology, it's self-contained in a tiny nozzle that the electrolyte is flowing within. And the key there is that the electrolyte is constantly flowing, so we're reducing mass transport and really making a consistent material during the deposition or during the growth of our part or material that we're putting onto a different substrate or a different part.
We decided to work on this research area to take advantage of the specific benefits that electro deposition offers. And those include high density materials, metals, the ability to modify material properties through changing process conditions. We can change conductivity, we can change hardness. But taking advantage of these different modifications of the material properties requires us to be able to fabricate devices out of those materials, and that's what was lacking in this space.
Electro 3D has a number of potential commercial applications. Solar cells, we can make electrical traces, high quality materials. Structural electronics, especially 3D structural electronics, where we could incorporate three-dimensional traces, wire bonds, and components into this compact three-dimensional electronic. Heat sinks for data centers where you need high quality materials to extract the heat. Thermoelectric generators, we're able to print the materials, which has never been demonstrated before, so we're creating three-dimensional thermoelectric materials, the thermal piles, and what we're able to do there is extract the waste heat energy, for example, from a data center and convert that into electricity. So we had a multidisciplinary team of engineers, scientists, all coming together to create a novel new technology, game-changing technology, and it wouldn't have been possible without the team and support that we had at Sandia to develop this game-changing technology. Okay, thanks for the video. General overview of the technology that was produced for our R&D 100 award as part of a trailer, just to introduce folks to what this technology is and what it has the potential to do. So the technology started as an LDRD. It wrapped up that that program wrapped up in 2022. We then participated in Energy I-Core, part of cohort 16. That's a DOE-sponsored program to help bring or transition technologies from the national lab system into industry. So that uh, myself and Mikey participated in that program, and that was to help us better understand potential opportunities for Electro 3D in industry and help us learn what it takes to, at least get an introduction to what it takes to bring technology from the lab into industry. So very valuable program. Help set the stage for the R&D 100 award, some patent applications, and then also for internal tech maturation funds that we're currently working through. And that tech maturation fund has come through DOE, the Department of Energy, OTT, part of the Energy I-Core graduate program. So we got some funding through that, and then also through tech maturation funding through Division 8000 of Sandia National Lab. So later on in the presentation, we'll talk about how that technology maturation fund is being used and what's been demonstrated through that funding. We are, or this technology is currently seeking partners, opportunities, or licensing applications to continue to mature the technology for, interesting opportunities or applications. So let's dig a little deeper into the actual technology here. So the LDRD program, it starts off with a proposal process, and luckily a proposal was awarded for the development of thermoelectric materials. That kicked off in FY20. So we started off with paper scratch of what this technology could be. And from that, we transitioned it within a couple months of having a functional or a demonstration of this technology. Now, very rough. Some of the first features we printed were fairly dendritic, rough surfaces, not super smooth. But we were able to continue to develop and grow and learn about this technology to refine the process to be able to eventually print columns of materials, so copper columns and thermoelectric columns. So the thermoelectrics, those were ternary materials, so bismuth, tellurium, antimony, bismuth, tellurium, um, selenium, so our N and our P-type materials, and we were able to grow those columns into pillars, and those pillars are part of a thermal pile for a thermoelectric device. Now, where we went from that, so the LDRD wrapped up in about FY22 with a patent application submitted, final presentations, and the technical readiness at the end of this program was around a 3.5 or so. So now, as we continue on, some of the exemplars from that LDRD program were the development of 3D structures. So these pillars again. So the pillar on the left is a copper pillar that's about 12 millimeters tall, and the height was limited by the stage translation capability that we had. And the width was defined by the nozzle print geometry. So it was about 400 microns. Now this 400 microns, that could be tuned larger, smaller, just depending on the application. However, for the thermoelectric material, we're focused in on that 400 to millimeter diameter thermoelectric pillars that was found to be optimal for our particular application. The middle is a serpentine type structure, so 2D serpentine, and what you're seeing is a gradient of thermoelectric material that was printed across using a different print speed here, or voltage or power that was applied to deposit the thermoelectric material. So a range of different ways that you control thickness of the material you're putting down. So a number of parameters that can be tuned in to produce, materials or structures that might be desired. And then our rightmost photo is a copper pillar being printed in real time. So the silvery metallic, that's the print nozzle, and that is printing a copper pillar about 1 millimeter tall and 400 microns in diameter. And what you're seeing here, so at the very start of the print, the meniscus was contacting the substrate below, and then as that structure grows, as the copper deposits, the structure grows up and the nozzle moves up. There's a feedback loop that helps with the automation of controlling the growth or the movement of the print head. And as it grows up, the meniscus grows or moves along that printed surface. And that meniscus, now compared to what's currently been published or in research as far as meniscus confined electrochemistry or meniscus confined additive manufacturing or 3D printing, is that this meniscus that you're seeing right here is actually flowing. So it's flowing to reduce inefficiencies in the deposition and to allow for uniform material properties to be deposited. That flowing meniscus also has other benefits. You can switch out uh, potential materials quickly, rinse. You can do a range of things by having the electrolyte constantly flowing. And this also allows for fairly smooth surfaces to be created, potentially shiny surfaces we've shown in instances. So you can really tune structures by tuning some of the flow rates and other parameters here. So let's go on to our next slide. So through Energy iCore, what that enabled us to do is understand market potential, so industry opportunities. And with this technology, we started off seeing just tons of interesting applications where it could be used, but not exactly knowing what within this industry was the most interesting or early adopters in these potential markets for this technology. So tons of potential, but finding those areas for this technology, um, I would say Energy iCore just gave us a glimpse into that. So we're hopeful, with this type of outreach, this presentation, that we'll get more interesting inquiries as far as like, oh, this could be used for that and this. So please reach out if you have suggestions or potential applications. We would love to hear your thoughts about applications of this technology. So within Energy iCore, we focused in on solar and in particular space solar cells because we saw an opportunity for 3D printed electrical traces. And what that could do is reduce manufacturing costs by one, eliminating the need for some of these lithography steps and potentially reducing the cost of materials for the electrical grid. So instead of using silver or silver copper or some uh, form of that, you could transition it towards maybe a nickel copper or nickel copper silver, and that would be electrochemically printed rather than maybe ink jetted or some other technologies. Uh, so we see there being a potential opportunity for both material cost reduction as well as manufacturing cost reduction, and in particular for the space PV market where these solar cells are subjected to pretty extreme environments, just depending on the application and the desire for having long life up there and constant generation of energy. The other interesting area for this technology is printed electronics, and in particular 3D printed electronics. So electronics are used in a number of different applications, from medical to satellites to rockets to automotive to solar. There's just a number of potential opportunities within the printed electronics market. for prototyping as well as production. And combining those two together, the solar, the printed electronics, well, there's aerospace, and aerospace kind of brings everything together. It's a market. If we go on to the next slide here, uh, that is ever accelerating. And within the solar cell market here, if we keep cruising, we conducted a case study within the solar cell market and looked at different manufacturers for putting down electrical traces. So there's inkjetting, there's physical vapor deposition, there's electrochemical deposition, there's screen printing, and in some instances, there's a combination of these technologies that are used to produce high quality grid lines for extracting that charge from solar cells and converting it into useful energy. What we saw here, what we captured from doing this market survey or just market analysis within Energy iCore was that although a number of these technologies hit like speeds, powers, costs, performance requirements, none of them quite can dial in all these different attributes as Electro 3D could. So a lot of interesting analysis was conducted here, but that's the main takeaway. So let's keep rolling. So looking at a 3.5 solar cell manufacturing flow chart, this was this flow chart I borrowed from NREL. They had a nice overview of 3.5 solar cell production. And what we're looking at here is that it's a multi-step process, and primarily where we're focused in on for Electro 3D, for where this technology could potentially insert itself and drive some cost reductions would be in the step 11 and 12, the metallization lithography step for the front metallization of those grid lines. So instead of requiring lithography to pattern the substrate to define where those electrical traces go, Electro 3D has the potential to define the electrical traces as well as put down high quality materials. So, combining some of these steps, reducing, eliminating, improving efficiencies of this 3.5 solar cell market at the same time, putting down some high quality materials that should be able to survive space-like environments. So let's keep going and take a look at the cost, just a, napkin type calculation here. So again, borrowing some materials from NREL, they had a cost analysis, cost per watt analysis of these 3.5 solar cells. And this chart shows that there's a significant cost with the lithography and the deposit of the front metallization. Now, if we are able to combine those two steps, let's take a look at what that will reduce the cost per watt for the solar cell. Well, if we're able to combine those steps, that saves us, over 10-20% just by the materials alone. So that's not necessarily looking at, are we eliminating the lithography step, but primarily just focused on that, the cost of materials. So silver versus copper, there's a big differential there. So just by changing materials, you can potentially save quite a bit. And that is a pretty significant amount when we're talking about cost per watt here. So let's keep rolling. So as mentioned, solar, there's increasing appetite to power satellites, and powering satellites, there's a number of companies out there that are looking to produce 3.5 solar cells to do that. Well, one potential edge some of these companies could have is to improve manufacturing efficiencies, reduce costs where they can be. So Electro 3D, may have an opportunity to help with that and provide a company producing 3.5 solar cells an opportunity to increase their market share. So again, this is a map, a hockey stick diagram showing the drivers of satellites, and it's ever growing and increasing with the demands that we have and current technology requirements that are driving it. So let's keep rolling. So if we take a deeper look into the TAM, SAM, SUM potential for this technology. So the space solar cell market currently about 3 billion, expected to almost double by 2030. That's huge, 600 billion. Within that, you got to power those satellites somehow. And 3.5s are good. There's other ways to do it too: silicon, ultralight silicon, thin film coatings, but they all are fighting for a piece of this pie. And within that, space PV market is gonna nearly triple by 2030 as well. So that's pretty big. And we figure that Electro 3D currently within that space is 2 to 20 million. So plenty of opportunity, in space and potentially even on Earth, but efficiencies as far as technology development would need to be increased to really be a significant contributor to this area. So the technology is a 3 to 3.5 or a 3.5 right now. With additional, R&D cycles, I would say it would be ready for insertion, but would need, company support or technology support to really drive it towards key metrics for that particular application. So it shows potential, but needs some industry industry mentorship or collaboration to really make it see the light. And now we're going to transition into a case study on printed electronics. So let's take a look at our next slide. So here we're showing a process flow diagram for creating printed electronics. You can see there's a number of steps, and it's a lengthy, very involved process with a lot of different technologies that are used to create the printed electronics that are used today, from smartphones to watches to computers to automotives or automobiles to airplanes, just a range of different applications. So not to dig into a hole there, but within this, we see Electro 3D as being a way to reduce the number of processing steps to create printed electronics, not only for prototyping, but also potentially for production, just to enable new designs that weren't feasible with current processing steps. So not only the integration of electrical signals or traces for digital and power type applications, but also the insertion of combinations of systems or transmissions from electrical to RF to optical to some hybrid system that communicates with a range of different technologies. So let's go on to our next slide here. And I'd like to thank the S2 Edge program. We had a couple interns working on evaluating the printed circuit board industry and understanding customer demands and desires within that industry. So these interns, they conducted a number of customer discovery interviews to understand what are some of the biggest challenges within the printed circuit board manufacturing industry or sector as a whole. So there's concerns of environmental impacts. A lot of this technology is moving overseas. There's a dependency on overseas machines and materials. A lot of these steps are complex and multi-step processes that require high-tech facilities and range of different processes that can be dangerous and use hazardous chemicals. To start up one of these companies, you're looking at 30 to 40 million just for the manufacturing facility and tools, and labor and all that other stuff would I imagine fold into that equation as well. production costs, material waste, prototyping and validation. We talked about qualification a little bit as well. So a lot of the qualification is, well vetted in this type of industry because it has or is uh, used by so many different applications and technologies that qualification is well understood. So let's keep going here. So I'll look at the market potential. So the printed circuit board market. So today, a fairly healthy number, $90 million, but in the next 10 years or so, that's expected to nearly double or increase pretty significant. And within the market itself, so there are companies such as Dragonfly by Nano Dimensions that are looking at creating and are creating 3D printed electronics. In 2008, it's my understanding their market was around $4.2 million. The possibility for technology like Electro 3D, and this is taking into account some of the analysis that the S2 Edge interns performed. It was estimated to be right around $14.4 million. So that's a pretty healthy size of resources or dollars to support the potential applications that this technology could serve. And it was really interesting quote by one of their customers that they interviewed was they said, as long as some of these problems or challenges can be addressed, they think it's only a matter of time for 3D printed electronics would be the way to create circuit boards in the future. So that's from an industry interview directly, someone located in aerospace and a defense company. So they're predicting, or they hypothesize that 3D printed electronics are going to be very impactful in the near future. So let's keep going. And some of the key takeaways from the customer discovery were that companies would potentially be willing to pay additional resources for having systems or manufacturing methods that are more environmentally sustainable. They maybe have a higher upfront cost, but long term they decrease some processes that save money in the long term. And also have the ability to replicate some material standards that are current in industry. So using maybe some of the same materials and same processes to be able to do that. And also the ability not only to prototype, but also to manufacture some of these boards. So having the agility or flexibility to be able to not only prototype, but then manufacture that at scale. And there is a bit of a hesitation to be the first in the industry, kind of the early adopter of some of these technologies, because you never know how stuff is going to work out. And the future for printed circuit boards and manufacturing, it just seems like there's a lot of potential here and opportunities for 3D printing in this industry. So let's keep going. And if we take a more focused or zoomed in view as far as competition and availability within the 3D printing market, and further look down within the 3D printed market and look within the 3D printing electronics market. So currently about 300 million by 10 years or so. It's expected to just increase pretty dramatically up to about $8 billion. For the US printed 3D printed electronics market, that's expected to be about 98 million or near 100 million. So significant long-term opportunities in this space. Again, technology for this opportunity is around a 3.5. Industry partnership, licensing would really help mature and develop this technology and tailor it towards specific applications within the 3D printed electronics market. This not only has the ability to prototype hardware, but could also potentially be used for production or editing hardware. And it could revolutionize designs for this field too, and process capabilities. So not only electrical, but we're talking RF and optical, and just a range of different systems that could be interesting to interconnect and bring together to create very complex printed circuit boards of the future. So let's keep rolling. We're not going to go down that and talk about our current developments and what we have been able to achieve with our tech maturation support that we've received from Energy I-Corps graduate opportunity, as well as Sandia's Division 8000 tech maturation funds. So first, starting from the left is hardware and software updates, and these were conducted or are being conducted to be able to produce demonstration hardware such as printed circuit boards and form factors that are relevant to industry today. So looking at printing on relevant substrates such as FR4, Kapton, silicon, and understanding some of the material specs as far as creating a design guide, a spec sheet that could help inform industry of this technology and potentially help with industry engagement and collaboration opportunities. So let's keep going here. So the hardware development, we're looking on the left side here. So the system has three primary stages, a gantry type system, and the printer is in the center-ish of that figure there. It's attached to a bracket that also houses a surface profiler. And below the printer is a substrate holder that allows for measuring forces and materials being deposited and such. The centermost diagram there is showing a bit of an eye chart, but it's our deposition pressure versus our vacuum pressure. So I mentioned earlier in the presentation that one of the key technology, uh, one of the new aspects of this technology is that instead of a static meniscus, this is a flowing meniscus. So within that flowing meniscus, it's driven by pumps and systems that allow for that meniscus to stay stable, but at the same time flow. So we're quality design control methods, as well as conducting design of experiments to better understand process printer parameters, material property structure, relationship towards understanding repeatability and reliability of this system. So let's keep going. Additionally, we're working on updating the software, adding in sensors to better control when things might not be printing quite correctly, and using artificial intelligence, machine learning to help optimize printing properties and printing parameters more quickly or more efficiently than what could be done. So we're driving in the latest as far as software and machine learning capabilities to hopefully help optimize and refine and be able to insert potentially new electrolytes and have that developed machine learning model and artificial intelligence help really refine the printing capabilities of that new material. So some of the next steps, we're performing additional experiments, again, to help drive and understand system design guides. We're reproducing these designs and reproducing the experiments to get reproducible results, and we're conducting additional analysis. This data will be fed into a machine learning model. So let's keep going. So in summary, just going through kind of summarizing exactly what we've done here is the lower left is a demonstration of the current printing technology, and what you're going to see is meniscus is formed, and then it's interacting with the substrate below, and you'll see a copper trace being printed in real time. So these are real-time videos. Printing, this first print is about 300 microns per second, and then it will do, or the video will show one additional print that's about at 500 microns per second. And then the centermost image, that's chip from one of these prints. These features are about 10 millimeters in length, and the variation in coloration that you're seeing there is transition from different power settings for the deposition, again, to better understand the actual deposition parameters and feed that into understanding optimal print parameters. So here, yeah, you'll see the printer transition to the next slide there, or the next printing line that it's printing. Again, Electro 3D, it's a technology that enables electrochemical printing, and it really reduces mass transport and inefficiencies that can happen if you don't have a constantly flowing electrolyte, especially as you're switching to different materials that might not be really acidic or really basic. Maybe your material is something in the middle. So this technology could help with producing or depositing high quality, consistent materials in a well-defined area. So we demonstrated this technology using copper, but there's a range of materials this could be good for, anything from metal oxides to semiconductors, biological materials to organic polymers. You know, they have to be tuned for electroplating or electrodeposition, but those materials are all feasible. And since this is flowing again, you can transition to a range of different materials. And since it's flowing, a flowing meniscus, it really eliminates inefficiencies in that deposition process, allows for consistent material deposition, and there is an opportunity to achieve high resolution features and structures. And right now, again, we're focused on printed circuit board technologies for wiring type boards, so not really ICs. And where we're focused in is around that 300 micron range to millimeter size widths. So Electro 3D, it's a technology that could help, revolutionize the printing of electronics and potentially other applications. So look forward to the interactions that we receive from this presentation. And before I hand it off to Debbie, I just want to say thank you to Jess and her team for helping prepare the slides. And the slides that you just saw were the primary work of Morgan Hamby, as well as Hannah Powers, that they conducted this summer as part of their internship. And that work was, again, supported through the Energy I-Core graduate tech maturation funding, as well as the Sandia Division 8000 Tech Maturation Fund. So yeah, thank you so much. And one more, I'd like to thank Mikey for the intro and partnership in Energy I-Core too. So Debbie, take it away.
Carl, thank you for that great presentation. I want to talk about some ways that you can partner with Sandia. As Carl mentioned, Electro 3D is available for partnering, so I just want to briefly go over some of those partnering mechanisms that we have. First is the Cooperative Research and Development Agreement, or the CRADA, and this is a collaborative R&D effort between one or more federal labs and one or more non-federal entities. Typically, these are longer-term relationships that can last for several years. In fact, we've had a CRADA with Goodyear that lasted for over 20 years, something that we're very proud of. Under this type of agreement, the participants can have a license option to any of the subject inventions for a period of up to 6 months after termination or completion of the work. And they can elect to get up to an exclusive license. All the background IP that is needed to carry out the CRADA is provided to the participant at no cost for the duration of that project. And we do about 40 to 50 CRADAs per year. Another mechanism is the Strategic Partnership Program. And these are really a work for other type of agreement where the participant is paying Sandia to carry out a specific scope of work. We can do this with industry, nonprofits, or other non-federal entities. We have a defined statement of work that uses Sandia's unique facilities, equipment, and personnel. And under this type of agreement, typically the subject inventions can be owned by the participant if they are a U.S. entity using private funds. And we do about 60 to 70 SPPs a year here at Sandia. Another mechanism is licensing, and we have a tiered approach to licensing to really help de-risk the licensing effort for the partner. So, the earliest level of licensing is really the test and evaluation. These are short-term evaluations to carry out non-commercial research and really test out the technology and see if it's something that the company wants to pursue. These can typically last from 6 to 12 months. And maybe up to 18 months, depending on some of the situational aspects. We also have the license option agreement. This gives a limited term to obtain a license. Again, these are research licenses, but at the end of the license option term, there is an opportunity from the partner to elect to obtain, again, a license up to an exclusive license. And we provide commercial licenses to patents and copyrights. Another way to work with us is through our user facilities. We do have state-of-the-art user facilities that are open to industry and academic partners, whether those are proprietary in nature, in which there would be a full cost recovery, or non-proprietary, where maybe it's just a publication that would support that effort between Sandia and the other partner. We do have a couple of specialized programs for companies in the state of New Mexico that I'd like to tell you about. One is called Trigger. It offers up to $150,000 worth of funding for research activities to be carried out at Sandia. This can be in the form of prototyping, proof of concept, or technical validation. And these are for New Mexico businesses that have an active CRADA or license with Sandia, and the work does have to be completed in 12 months. Another program is the NMSBA program, or New Mexico Small Business Assistance. Depending on where you are located in the state of New Mexico, you can be awarded up to $40,000 of research assistance through Sandia or Los Alamos National Labs. And this is for any small businesses paying gross receipt taxes to the state. And we're very much interested in partnering with any type of entity, whether you're a commercial business partner, a university, government, or another federal lab. So we are looking to advance this technology, to really further the research and development, demonstration, and deployment of this work. So please do reach out. Next slide. Electro 3D is one of the many amazing technologies that we have here at Sandia National Labs. I do encourage you to go to ip.sandia.gov, where we have over 1,800 commercialization opportunities available. I support a lot of the bioscience, chemistry, materials, advanced manufacturing, and I'm happy to support any inquiries in those areas, or you can please contact me as well, and I can reach out to colleagues that may handle other portfolios of interest. But again, please do check out our website at ip.sandia.gov and look for some additional technologies that may be of interest. Thank you so much for your time today.